In this video, we'll look at exponential decay. The equation I've given is y equals 5 times 1/2 to the power of x. So, we can tell it's exponential decay because the base or ratio here is between 0 and 1. 1/2 is 0.5. That's obviously between 0 and 1. That's how we know it's decay. Nonetheless, we work with it the same way we work with exponential growth, which is we identify the y-intercept based on the number in front here, and that is 5. So we write 0 for x, the y-intercept x is 0, the y is 5. For the start value, that's the y-intercept. It's literally this number in front. It's the a value, which is a 5. And the change is this ratio or base, which is 1/2. You can write a half or 0.5, whatever's easier for you. Those properties were easy. We just look at the start value or the a value, that's 5, and that's also our y-intercept. And the thing in the brackets with the exponent, that's our change or base or ratio, which in this case is a half or 0.5. We can do domain and range now, but it's easier once we've graphed it to look at it and see. So let's graph it by making a table of values. I'm going to use my calculator to do that. And I'm going to start with 0. I'm going to do a half or 0.5 to the power of 0. Oh. And I hope you can do that in your head, because you should know anything to the power of 0 is 1. Times that by 5, and I get 5. Okay. 0.5 to the power of 1 now. Again, something you can do in your head. That's just 0.5 times 5, and I get 2.5. I'm just subbing into my equation. So now sub in 0.5 to the power of 2, and times that by 5, and I get 1.25. And now sub in 0.5 to the power of 3, and times that by 5, and I get 0.625. Okay. You might notice a pattern here that it's going down by a half. That's because of the ratio. It's times by 0.5. So if you can see that pattern, it's times by 0.5, times by 0.5. You should be able to predict what this number is going to be. Let's see. 0.5 to the power of -1 equals times 5. You get 10. No surprises there. It goes down by a half, or timesing by 0.5. So if we're going backwards, it should go up by the same proportion, but in reverse, so times by 2. Let's see it again. 0.5 to the power of -2 times 5. You get 20. I bet you can predict what the next one's going to be. I'm thinking 40. Let's see. 0.5 to the power of -3 is 8 times 5. Is 40. So do you have to show your work? No, you can just put an 80 here. You know what the next one's going to be. It's just to show you 0.5 to the power of -4, and then times by 5, and you get 80. We've got our x and y values for our table. Now let's calculate the first differences. When you're doing first differences, it's always the second number minus the first number. I always go this minus this. What's 40? Take away 80. That's -40. So often students will do it backwards and go first minus second. It's always the second thing, take away the one before it. 20 minus 40, and you get -20. Look at that pattern. See another pattern coming up? 10, take away 20. That's this, take away this. I get -10. So looking at that pattern, I bet you can predict what 5 take away 10 is, even if you can't do it in your head. You can use your calculator, or better, predict the pattern. -5. So you know what's coming next, I bet. What's 2.5, the second number? Take away the first number. -2.5. And again, if you see the pattern, you can just write the numbers down. 1.25 minus 2.5 is -1.25. And even though this I probably couldn't do in my head very quickly, but I see the pattern. I know what this number is going to be. It's going to be -0.625. And I've got my first differences. So how do you calculate your ratio? Same sort of work, except it's second number divided by the first number. what's negative 20 divided by negative 40? The ratio is 0.5. And that should come as no surprise. We already identified the ratio or the change to be 0.5. Again, if you can do this in your head or see the pattern, you can stop using the calculator, but it's okay to use the calculator. Negative 10 divided by negative 20 gives me 0.5 again. What's negative 5 divided by negative 10? I get 0.5 again. Each one is halving. Let's see it again. Negative 0.25. Oop, a couple typos there. Divided by negative 5. Again, 0.5. They're all going to be 0.5s. Let's do the last two just to be sure. But I'm sure. Not just because I've done it before, but because I can see the pattern. 0.5. And I also knew from the equation what the ratio would be. This second one, 0.625 negative, divided by negative 1.25, and I get 0.5. There's the ratios. We just wanted to look at this to show, I particularly wanted to show you how to calculate the ratio. If you weren't given the equation, just given the table, there's the ratio appearing. But we knew it because we had the equation. What we really want to do is graph these x and y's. So I had a graph prepared here. Notice I put my arrows and I labeled my x and y. I labeled all my little ticks and I labeled at least every second tick with a number. Now I'm going to put my points. Obviously a lot of them don't fit. Negative 480 would be way off the page. So would negative 340 and negative 220. I can't possibly graph those. Negative 1, negative 10 is just off my graph. But it's somewhere up here. Just about there. So I'll start with 0 on x, 5 on y. And now 1 and 2.5, so that's halfway between 2 and 3. And then 2 and 1.25, just above the 1. And then 3 and a little more than halfway to the 1.625. Okay, so I know it's going to go up forever and still going left, so I'll put an arrow up here. The reader can see it. And then come down through this point in a nice curve through my next point and through my next point, and then close in but never touch that x-axis. This is a classic shape for decay. They always look like this, super steep in the beginning and then they level out, they come in for landing but never touch the x-axis. That's an asymptote. It's a line that an equation, in this case an exponential decay equation, approaches but never touches. That's an asymptote. And in this case the asymptote is the x-axis, or y equals 0. That's going to be important in a second. Well, let's start with domain. Even though it's super steep, you can still keep subbing in negative numbers. You could do negative 5, negative 6, negative 7, all the way to negative infinity. It would be super steep, but it would exist. In other words, you can never stop going left. And this equation also never stops going right. That's why the domain is x, the set of x is an element of R. The x's can be any real numbers. Anything goes. The y is a different story. It never stops going up. It goes up to infinity. But as it comes down, it levels out and approaches but never touches this asymptote I was talking about, which is at 0. So what's the lowest you can go? Infinitely close to, but never touching 0. How do we express that? The range is the set of y is an element of R such that the y's must be greater than, but not equal to, 0. And we've done it. We looked at exponential decay. We started with an equation, and from it we calculated the y-intercept, the start value, and the change value, or the ratio. And then before we did domain and range, we made a table of values. We were given some x's, calculated their y's, and then we found their first differences in ratios just to see how that worked, where the ratio comes from. We used the x and y values to graph, and from the graph we were able to easily see the domain and the range.